Welcome. Today's lesson is on choosing the right Q or heat equation. Before you watch this video, make sure you've already watched the specific heat video and the boiling point video. This is the third in the series, so make sure you watch the other two first. So, from the other two videos and from discussions in class, you should recognize these three equations. The first one, Q equals MC delta T. The second one, Q equals M delta H. And the third one, Q equals N delta H. And now we're going to talk about when do you use these equations. And this is kind of like when we did the gas units. You had several equations, PV equals nRT, or P1V1 over N1T1 equals P2V2 over N2T2. But you still needed to know when to use which equation. Just like this unit, you'll have multiple equations and they'll be given to you, but you still need to know when you use each one. So the first one is used when there's a change of temperature and the material stays all as a solid, all as a liquid, or all as a gas. So there's no melting or boiling going on if you're heating it, or if you're cooling it, there's no condensing or freezing going on. The material must be in one state and only one state. So it can't change. If it doesn't change, it's at one state, then you use Q equals MC delta T. But what if it does change a state? Well, if it does, then you're going to use one of these two equations. And notice they're very similar, except one is M delta H and the other is N delta H. And so M stands for mass, and it's in grams, and N stands for number of particles, and that is in moles. So how do I know which of these two equations to use? Well, as I said, you're going to use one of these two equations when you're either boiling or freezing or melting or condensing when you're changing state. And if the delta H is given to you in like joules per gram or calories per gram or kilojoules per gram, some energy per gram, then you're going to multiply it by the mass so that the grams will cancel. But if the delta H value is given to you as joules per mole or kilojoules per mole, then you would multiply by moles because we're going to still be aware of our units. So if it's changing state, we got to use one of these last two equations. Now there's one other thing you need to look at is the delta H. We have two types of delta H's for heating and cooling, and that's the delta H of V, which stands for vaporization, and the delta HF, which stands for fusion. So when do I use delta H of V? That's when you're either boiling or condensing at the boiling point. When you are using delta HF, that's when you're fusing something or freezing something. Or it's also the same number that you use when you're melting something. So those are three equations. The first one you use when it's one state. The second one, when it's the second two, is when you're changing states. So let's practice this after I've kind of told you this. So get out your problem book. So pause the video and go to problem book 905 and actually put the answers. I'm going to do a couple problems from 905, and you want to put these as examples in your problem book. Thanks for getting your problem book, and I've paused and waited for you, and now we're ready to go. So on problem book 905, I'm looking at problem 7. And before problem 7 starts, there is a list of all of these values. So it gives you the C values, the specific heat values for nickel. And notice it gives it to you for the solid, it gives it to you for the liquid, and it gives it to you for the gas, and they're different numbers. It also gives you delta H of fusion, which we use if it's melting or freezing, and delta H of vaporization if it's boiling or condensing. And you might want to think, how can I use the same value for melting as I do for freezing. Well, they're just opposites, right? So the energy that is needed when you melt something is the same energy that's given off when you freeze something. So they're just opposites, and then we give a negative sign to the exothermic, which is the freezing part. So, and what else is given to us? Well, they give us the melting point and the boiling point. So let's try one of these examples, and let's do 7a together. And 7a says, calculate the energy change when a coin made of 5 grams of pure nickel is melted at its melting point. So now we need to pick one of those first 3 equations to use. So let's go back to them. And it's changing state. So I'm going to use one of these 2 equations at the end because it's not staying as a solid, liquid, or gas. It is changing. It is melting. So I'm going to use one of these. And if I know it's melting, I'm going to use the delta H of fusion if it's melting. All right, so now I have to figure out, do I need to multiply by mass or by moles? Well, let's look at the material it gave us. So delta H of fusion for nickel, this time it's given to us in joules per gram. So I'm going to need to multiply it by grams. So I'm going to use this equation right here. So the first thing you do is write the equation down. So it's Q equals M delta H of fusion. So I know it was the fusion one because it says the word melting twice. So I know I'm going to use the melting one, which is fusion. I can use that for melting or freezing. And I'm going to use the mass one because it was given to me in joules per gram. And that number, once again, is 297.1. So delta H of fusion was 297.1 joules per gram. So now I just plug in my numbers. So the math for these is pretty simple. Once you've picked the equation, the mass is 5.00 grams. The delta H of fusion is 297.15 joules per gram. The grams cancel, so I get out my calculator, and that's how I know I've picked the right formula, because I have to be aware of my units. If these did not cancel and I didn't get joules, then I know I have chosen wrong. So I need to get out the calculator, and I get an answer of 1,485.5 joules, but that's way too many sig figs. I only need 3 sig figs. So 1, 2, 3, I've got around here. So this is more than half, so it's going to be 1,490 joules. Or if you want to, you can report that in kilojoules, which is divided by 1,000, and I get 1.49 kilojoules. Okay, so there we have our answer. We picked the right equation, we plugged in our numbers, we solved it, and we put it in the right sig figs. So let's try B of that problem. We're going to find the energy that is needed for a vat containing 1,250 grams of liquid nickel at 2,001 degrees Celsius, and this is cooled to 1,501 degrees Celsius. So what I notice is that I'm in liquid form, and I'm cooling it. So did I cool it enough to freeze it, to turn it back into solid nickel? Well, previously it told us the melting point, which is also the freezing point, was at 1,453 degrees Celsius. Did I get that cold? No, I'm still up at 1,501 degrees Celsius. So it's a liquid, it starts at a liquid, it stays as a liquid. I'm not melting or boiling or freezing or condensing. So that gives me the very first equation, which was Q equals MC delta T, our friend. So once I've picked the right equation, and I'm going to remember that the C needs to be for the liquid because I'm in liquid form. I'm going to plug in my values then. So Q equals M, the mass is 1,250 grams. The C value for this, let's go look that up. The C of the liquid is 0.732 joules per gram degree Celsius. Oops, and just as I'm scrolling down, I forgot what that says, 0.732 times 0.732 joules per gram degree Celsius. And the change in temperature is 500 degrees Celsius. And I'm going to put a dot there because I can go to the ones place when I subtract these two numbers. So that's degrees Celsius. And this was a 3, in case you can't see that. So then once again, I get out my calculator. And I've chosen the right equation because you can see the units all cancel. And I use the right specific heat. So 1,250 times 0.732 times 500 equals 457,500. But once again, way too many sig figs. I only need 1, 2, 3 sig figs. 1, 2, 3. I've got to stop here. So I get 450. I'm going to round up 8,000 joules. And that also converts to 458 kilojoules. So either of these two would be correct if the problem doesn't specify what your final unit has to be. It could be either in joules or kilojoules from that problem. So hopefully you wrote those down. If not, rewind and write the answers so you have some to look back on while you do these in class. So now it's your turn. Go ahead and finish on page 905. Do problems 6, A, and C. And then since I did A and B, go ahead and finish problem 7, C, and D. And give it a good try. I hope you do well, and thanks for listening.